Okay, good morning. So let us continue the lesson. We want to discuss about the vectors, but from an analytic point of view, yes? So the first thing that we want to do, we want to introduce vectors by numbers, and then probably it is easy for you to understand that if I want to present a vector by numbers, it is better to express how much we are displaced by that vector along the x direction, how much we are displaced along the y direction, and how much we are displaced along the z direction. And of course, these numbers could be positive, negative, or zero. If it is positive, it means that we are going to the positive direction of that corresponding axis. And then if this is negative, we are going the opposite direction. And if it is zero, it means that we are not actually moving along that axis at all. Yes, that's a very simple thing. So from now on, a vector for us is like a number, a triple of, like a point is a triple of numbers. Yes. So I would say that, for example, vector A is equal to a triple of numbers. I would say A, B, and C, and then A, B, and C are real numbers, and as I told you but they are not called the coordinates of the vector, they are called the components of the vector to differentiate it from the vector. So I will use a triple for a vector and for a point, but for a vector I put equality. If I mean a point, I write it like this, for example. So I read it, the point A whose coordinates are A, B, and C, but then I will read this one, the vector V, whose components are A, B, and C. So that's the difference between them. And of course, in general, there is no connection between these numbers that you see here and the numbers that you see here. The interpretations are quite different, yes? So when I see, for example, a point A with coordinates 1, 2, and 3, it's just a single point in a space whose x coordinate is 1, its y coordinate is 2, and its z coordinate is 3. But when I write v equals to this triple, it means that this v, it doesn't matter where I start. Wherever I start, this vector moves me 1 unit along the positive x direction, it moves me 2 units along the positive y direction, and it moves me 3 units along the z positive direction. Yes? So the starting point is not relevant. Is there any connection between this vector and that point? I would say only when you draw the vector from the origin. If you draw the vector from the origin, what do you think will be the connection between these triple for the vector and that triple for a point? Yes?
It will go from the it will go from the origin to the point.
Yeah, so the tip of the arrow have that coordinates. But except for that, there is not a, so usually that is called the position vector. So if I have these 3 dimensions, this is x and y and z, and if I have my vector here, drawn from the origin to that point A, whose coordinates are A, B, and C, in that case, you can also say that V has the same components. Yes? But otherwise, if I start parallel transporting this vector, by the way, it's very important to understand, from a geometrical point of view, if I parallel transport a vector, the vector is not changed. Yes? That is the definition of vectors. So do you think if I parallel transport the vector, the components of the vector will change? If that is the case, we are in trouble. Yes, because on the one hand, from geometrical point of view, we realize that if that was the definition, if I parallel transport a vector, that would be the same vector. But if I now, in this new perspective, if I parallel transport a vector, and it is supposed that the components change, then I will be in trouble, yes? That there would be a discrepancy between this new perspective and the old one. And I hope that you agree with me, it doesn't matter, yes? If I just move this vector, parallel transport this vector, and draw it from any other point, the components will not change, because that vector again takes me A units along the x direction, B units along the y direction, and C units along the z direction. So that is important to understand. I want to understand that I want to repeat everything, but I'm not defining a new thing. Okay, I want to translate everything we learned about vectors in this new language. So this is important to understand. I'm not introducing again a new rule. For example, if I tell you add two vectors, I have the same vector addition in mind, yes, the same operational process that I have to parallel transport one from the tip of the other one and then find the third. So that is exactly the same, but that was geometrical, I have to draw shapes and things, but I want to translate the same thing in this new language, and I see that what will happen. Is that understandable? So that is the strategy we are going to follow in this lesson. And actually, it's a very good thing that to learn. If you go to technical universities, you really, really need these subjects. Okay, so let us see where I'm supposed to start. Not missing anything. Okay. Let us, for example, test your understanding a little bit. If I have a vector which is perpendicular to the z-axis, yes, what can I say about the components of that vector? Can I say something generic about the components of a vector? That vector is perpendicular to the z-axis. By the way, even if I choose one single point, first of all, I want you to understand, if this is the z-axis and this is the line, all of these lines are perpendicular to this. But in a space, these two lines are also called perpendicular. Yes? So be careful. So these two lines are also called perpendicular. If they are not intersecting, I choose one point on this line and draw a parallel line. So it means that I am also parallel transporting apparently. And then if they are 90 degrees, if they make a 90 degrees angle, then it means that they are perpendicular. So in this case, these are also perpendicular. Now I'm assuming that this is the z-axis, and this is a vector, okay, which is perpendicular to the z-axis. Can I say something about the components? Yes?
Its z value is 0.
The z value is 0. Is that clear? Because it will not it will not displace me along the z direction at all. So if I have a vector which is perpendicular to the z-axis, definitely the z component of the vector is 0. And if this is perpendicular to the x-axis, what will happen? The x coordinate will be 0. Sorry, the x component will be 0, and the other one, the y component, will be 0. So what about if I have a line, if I have a vector parallel to the z-axis? Can I say something about x and y z components of the vector?
The x and y are 0.
Yes, because if it is parallel to the z, it is automatically perpendicular to x and y. Is that understandable? Even if it's not, okay. So it will be perpendicular to x and y. So according to the previous argument, the x component should be 0, the y component should be 0, but the z component might be something, depending to the length of my vector. Okay, and if that is the tip of the arrow, the z component is positive, yes? Because it is taking me upwards. And if the tip of the arrow is here, that would be negative. So these things are simply understandable, yes? So for example, if that's the coordinate system, I don't know if you can imagine, this kind of vector, what are the components, positive or negative? So I don't know if this is a good way. So assume that this is your coordinate system. This goes y direction, z goes upward, and x comes out from the board. If I have this, do you think that, what about the signs of the, and this is the tip of the arrow for the vector. So is the x component positive or negative?
I think all of them is positive.
All of them are positive. So I am still here, but I turn it down. What will happen? X and y and z, positive or negative? Yes?
Only z is
Yes,
negative.
x and y are positive, z is negative. So it's easy to imagine what are the components of the vector. Okay. Let us talk about Do you remember? Let us review whatever. When I introduced the notion of a vector, the first thing that I introduced for the algebra of vectors is to define when two vectors are equal. The vectors are equal if they have the same length and they point to the same direction. Parallel and pointing to the same direction. Now, in this new language, it is much easier for us. If I give you two vectors in the analytic approach, it means that I give you two triples of numbers. So when do you think these two triples should be the same? Yes?
When all the numbers are equal.
Yeah, components should be correspondingly equal. So you see, but this is not a new definition. You see, I want you to understand. So if I have V, let me write. V is equal to A1, B1, and C1. And let me call U to be A2, B2, and C2. Then I would say that U is equal to V if and only if A1 is equal to A2 and B1 is equal to B2 and C1 is equal to C2. I want just to test your understanding. Is this a theorem or a definition? Now, theorem is a claim that needs proof, but definition is something that I just define and I don't need to prove. At this level, can I call this a definition or should I call it a theorem? Yes?
A definition, I think.
So, if I want to call it definition, then I had another definition for equality of two vectors. So it means that you have two definitions for the same concept. So in principle, it's not definition, because if I have two definitions for the same concept, mathematically I have to prove that they are equivalent. Is that understandable? Because I am defining the same concept in two different ways. So at the end of the day, I would call it a theorem. Because even if I want to call it the definition, I have to prove that this definition is equivalent to the old definition, yes? So then I will call it a theorem. So this is not a definition. This is equivalent to our definition of two vectors being equal, meaning that they have to be of the same lengths and they have to be parallel and pointing to the same direction. This mathematically is equivalent to that definition, so I will say that the definition of equality of two vectors translated in this analytic approach will give me this. Yes, I want you to understand. So this is very easy. So this is much easier than the geometric method. Yes, in geometric method we have to know that they are parallel, they have to be of the same length, but here I just compare the numbers. That's it. Yes? So that is the first thing that I want you to know. So from now on, either you want to call it definition or theorem, it doesn't matter, you can just use it. But I want you to have a deeper understanding of this. Okay, now another one. What will happen if I want to add vectors? Okay, so if I give you these two vectors and I ask you to add them. In geometric approach, U is an arrow, V is an arrow, and then we know how to find the arrow of the U plus V. Yes, we know how to do that. But in this language, I want to see how this will be, how the definition translates itself into this new language. Yes? So, for example, if I give you U to be 1 and 2 and 3, and let me give you V to be 2, minus 2 and 5. Yes? So, what is the role of this vector? This vector displaces me 1 unit parallel to the x-axis and in the positive direction. This vector actually displaces me 2 units. So do you think if I add these two arrows, what will happen for the sum? Yes? So let me for example, if in 2 dimensions I draw a vector for you. So here you have vector, for example. Let me make it 2-dimensional, it's easier for us to understand. So if this vector, this is 1, this is 2 and 1. So let us consider that this vector is u. And then I will give you another vector which goes 1 unit to the right and 2 units upward, yes? So this is 2 and this is 3. So I draw this from here. 1 unit upward and then 3. Something like that. So you see, if I ask you what are the components of u, you see that I am taking 2 units to the right by u. So x component is 2. And I am being taken 1 unit upward, so this is 1. And if I ask you what are the components of this vector, so let me call it v, then you will tell me that I am taking 1 unit to the right by v, so the x component is 1 and 2 units up, so that is 2. And now if I add them, not using this method, there's only one method to add the vectors, and that is this vector. So this blue vector, by the definition of the addition of two vectors, is the sum of these two vectors, yes? And if I ask you now, look, and can you read the components of this u plus v? Just read it from the picture, not any rules. How many units I go to the right by this blue arrow? So this 2 units and 1 unit, it is 3 units, yes? And how many units I am going upward? I'm going 3 units up, yes? So you see, I am reading the components of this u. And now what is the connection between this one and that one? It is very simple. The x components are added, the y components are added. So you see that working addition of vectors becomes very simple, just adding components. But I want you to understand, this is not definition. I am using the old definition of addition of vectors, which can translate itself in the language of adding components. Is that understandable? Okay. So from now on, you see working with vectors becomes very easy. If I want to add them, you need to convince yourself about these things because they are very simple. I don't want to spend so many time. So just so much time. So it becomes A1 plus A2, B1 plus B2, and C1 plus C2. So that is the addition of vectors is very simple now. Just add the components corresponding. And what do you think about subtraction? The subtraction will also be the same. Yes? And if I multiply my vector by alpha, what is your idea here? Alpha is a real number. So what will happen? I might just multiply the components by alpha. So simple. But you have to convince yourself that they are exactly according to our definitions. So this I will leave for you. And by the way, what is the zero vector? What is the zero vector in this new language? Zero vector doesn't take me, it doesn't display me at all, but so it means that this should be 0, 0, and 0. So that is these are the components of the zero vector. So do you remember what operations we had? What operations we had? We had addition, subtraction, multiplying a vector by a number, and also we had the zero vector. So these are just simple operations that we have. And if I ask you, what is the length of this vector? If I give you the components, so I don't know why I call this one, but so I have to be careful, sorry. So here A1 plus or minus A2, so if you don't mind, let me write this U and fix it because I was automatically using it in this way. Yes. So this one is U, this one is V in the vectors that I have written here. So if I ask you what is the norm of vector U, I think you immediately get this number. A1 squared plus B1 squared plus C1 squared. Yes, is that understandable? So I can immediately find the magnitude of the vector if you give me the components of that vector. Okay. One thing that I want to add is this one. So if I give you 2 points, not vectors, if I give you 2 points with coordinates x sub a, y sub a, and z sub a, and b, x sub b, y sub b, and z sub b. I have 2 points, and of course I can connect these 2 points and put, for example, the tip of the arrow on b, then I generate a vector. So my question is that if this is the vector AB, so you see that if I give you 2 points in space, yes, point A, point B, I can connect A to B and then put the tip of the arrow on B and generate AB as a vector. But in this new language, every vector corresponds to a triple of numbers. Yes, my question is that if I give you the coordinates of the points and I ask you what are the components of the vector AB, what I'm supposed to do? So it means that I'm asking you how much I am displaced along the x direction by this vector AB. And for the, yes?
You subtract b, the point, the x coordinate of b,
Yes.
by a.
Yes, so it means that the final point minus the initial point, yes? So I can, that's completely right. So that's important to know. So if I want to construct a vector AB out of the coordinates of 2 points, then I have to subtract the initial point coordinates from the final point coordinates. So it means that I have to write xb minus xa as the x component of my vector, and yb minus ya, and then zb minus za. It's a very important formula. Yes? Yep?
I might be confused of the zero vector.
Yes?
What's the difference between a point on the graph and the zero vector?
There is no difference here. So there is no difference here in this case. Of course, the zero vector can be everywhere. When I say the coordinate is 0, 0, 0, that's just the origin. I cannot move the origin if I consider it a point. But I can have the zero vector everywhere in space. Yes, that's the point. Yes? So there is no location associated to any vector. So even if I write it in the component form, that is exactly location-free point. Yeah? So you can have it everywhere. Okay, so here, this is AB. And why is that? For example, you can imagine AB to be the origin B. Do you remember? This is not something new. We knew about this before. Every vector, I can bring in any arbitrary point that I like, for example, in this case, O, and write OB minus OA. But finding OB is easy because this vector is being drawn from the origin. And I told you that the components of the vector corresponds to the coordinates of the final point if I draw it from the origin. You see, if I draw it from the origin, what happens? The coordinates of the tip of this vector are exactly the same numbers as the components of the vector. So this means that if I ask you, can you tell me the components of vector OB? Because O is the origin, in this case, I take these numbers. Yes? So instead of that, I can write xb, yb, and zb. Yes? And then minus the same story here. xb, xa, ya, and za. And this is a vector, that's a vector. I learned how to subtract the vectors. So that becomes exactly that expression that we got there. And then do you remember yesterday we talked about the distance formula. Now, and then if you want to calculate and understand the distance formula, you need to imagine and draw pictures. But here it is easy. If I ask you what is the length, what is the distance from point A to point B, I can solve it vectorially. I can find a vector and find its magnitude. Yes? If I ask you what is the magnitude of vector AB, you have a relation for that. Yes? This is exactly according to this rule. So you need to square the components, add them, square root. So if I do that, I will get exactly the distance formula we had before. So we can find those things easily. Okay. Let me see. Okay, we are done here. So, very, very simple example. Yeah, let me just do that. example. So let vector u be this vector 1, minus 2, and 5, and vector v be this vector minus 2, 4, and minus 6. Determine the norm or the length of 2u minus a third v. Yes? So we want to determine the norm of this vector. So what I'm supposed to do, if I want to find the norm of a vector in analytic way, there's only one way. I have to know the components of my vector and use this formula. So it means that I have to find the components of my vector, but that is a very, very simple algebra. So what I do, so 2u minus a third v is equal to, I multiply u by 2, so it becomes 2 minus 4 and 10, minus, I multiply v by a third, it becomes 2 minus 2/3, 4 over 3, and then minus 2, and then I subtract them. So then it becomes 2 minus minus 2/3, so it becomes positive 2/3, it becomes 8 over 3, and then minus 4 minus 4 over 3, so it is minus 16 over 3, and then finally 10 minus minus 12, 2 is 12. Am I right? And then I want to calculate the norm of this vector. So be careful, you are not allowed to take the norm of this one, the norm of this one, and subtract them. We discussed about this before. So I have to calculate this number. 8 over 3 squared minus 16 over 3 squared, and then 12 squared. I don't want to spend time on it. You square it and add them, take the square root, you get a number. And then keep it like that because we want the exact number. Okay. Now, I want to ask you another question. So let me write it here. So let u be this vector, 2, 3, and minus 1, v be this vector, 1 and 1 and 0. If w is equal to 2u minus 3v, determine, do you remember this notation? E hat of w. So that means, if you remember, it means the unit vector along w pointing in the same direction as w. So every vector that I have, for example, if my vector, the length of my vector is larger than 1, then if I ask you what is the E hat w, it means that that is the unit vector on w, yes? This is 1 unit length, yes? And this is called EW. And it is important. So whenever I give you a vector, in principle, you should be able to give me the unit vector on that vector. Okay, of course, if the vector itself is shorter than 1, then the unit vector becomes larger. So the unit vector is always 1 length unit. Yes? So, do you remember what to do here? So, of course, there is a formula for that, but you really don't need to work hard for your memory to find a formula. How should I find EW? This is called normalization. I want to normalize my vector. Normalizing my vector means making it of length 1. Okay. So what was the method to make a unit vector out of a vector? Do you remember? You don't need to remember, just think about it. So I want to make this vector on this vector and in the same direction, but I want to make the length 1 unit. So what should I do? Yes?
Maybe there is a faster way, but you can use the distance, the norm of the vector v and put it to 1, and then you calculate 2u minus 3v and all the...
Okay, let me first do that part you said. I calculate w. So calculating w shouldn't be any problem for me. It is 2 times u, so I multiply the components of u by 2, so it becomes how much? It becomes 4, 6 minus 2, and then minus, I multiply the components of v by 3, so 3, 3, and 0, and I subtract them, so I got my w. So it becomes 1, 3, and minus 2, am I right? Yes. Okay, then what?
then you square them and add them and then take the square root.
Okay, so you mean that find the norm?
Yeah.
Yes, I find the norm, but still it's not enough. I want to hear from you. So the norm has a formula. I have the components of my vector. Calculating the norm is very simple in this language. So it becomes 1 to the power 2, 3 to the power 2, minus 2 to the power 2, 10 and 14, yes? That's the square root of 14. Then what?
Wait.
Any one of you can participate. So how should I make that unit vector? Because this unit vector is parallel to my vector, that's for sure, yes? So it should be a multiple of that vector. So it means that E, W, E, you shouldn't expect something very strange. It is parallel to my vector, and it is in the same direction. So it should be a multiple of my vector. Yes, it should be a multiple of my vector, and this multiple should be a positive value because I want to have them the same direction. Yes, Ruben?
1 over the norm.
1 over the norm, yes? So that is important, remember this. So this question mark here is 1 over the norm. Why is that? Let us discuss, because that's important. Remember this. Okay, why this is what I need. First of all, this vector that I have introduced here is a number multiplied by w. So definitely it is parallel to w. On the other hand, this number is definitely positive because the numerator is positive, the denominator is the norm of a vector, it cannot be negative, so it's positive. So it's a positive multiple of my vector. So not only this vector is parallel to w, but also in the same direction. But then the point is that, is the length of this generated vector indeed 1? The answer is yes. Yes, because if I ask you what is the norm of this vector, do you just review this? If I want to find the norm of this vector, I have to find the norm of this vector. But then, do you remember, if I have a number from the norm, I can make it absolute value and bring it out, but I don't need absolute value because that's positive. And then I just take the norm of my vector. But now, if I ask you what are these are just simple numbers. 2 times 1 over 2. Any number multiplied by its reciprocal definitely becomes 1. So this vector is parallel to w, it's in the direction of w, and its norm is exactly 1. So that is exactly the vector that I need. Remember this fact. So then I calculate EW. So what is EW? It is 1 over square root of 14 multiplied by w. 1, 3 minus 2. So if I want to answer this, finally it becomes 1 over square root of 14, 3 over square root of 14, and then minus 2 over square root of 14. That is the unit vector. Yes? So these are important, simple but important. Let me give you another example. I want to wait for you to solve it, okay? Example. This is very simple as well. let we have this vector. For example, vector u is equal to 1, 2, and 3. The components are 1, 2, and 3. Determine a vector v that is parallel to u, whose length is 15. And whose length is. Okay, I want to wait a little bit. This is a very, very simple problem, but I want to wait for you. Okay? How should I solve the problem? First of all, can you guess how many vectors are there with that property? Before solving the problem. I'm looking for a vector that is parallel to u and its length is supposed to be 15 length unit. How many vectors do you expect? Yes, Robert?
2, I think.
2? Why?
Because one in the positive direction of u and one in the negative.
Yeah, so if you can find one, definitely you can find the other one as well, yes? So definitely there are 2, and then you know that the answers should be opposite to each other. By the way, I forgot to say, if I want to find the negative of a vector, it is -1 times my vector. So it means that if I want to find the negative of a vector, I just change the components from positive to negative, negative to positive, yes? Okay, so here, but how I solve the problem systematically? Do you have any idea? You want to have V. The claim is that the demand in the problem is that V is supposed to be parallel to U. Yes? But there are 2 things about being parallel in the geometrical point of view. Can you repeat them because they are important? If I tell you that 2 vectors are parallel, in principle you can conclude 2 equivalent things differently. So one of them, which we learned first, is one of them is, yes?
One is a multiple.
One of them is a multiple of the other one. And the second alternative, 2 vectors are parallel if and only if so let me repeat these. 2 vectors are orthogonal if and only if, because these are very important, these are anchors of this course, so you shouldn't forget about them. 2 vectors are perpendicular if and only if.
Is it that the cross product becomes the 0 vector?
Answering the first question or this question?
The first question.
Yes. The perpendicularity has something to do with the dot product. 2 vectors are perpendicular if and only if the dot product is 0. 2 vectors are parallel if and only if the cross product is the 0 vector, or you can say that one vector is a multiple of the other one. So both alternatives are important for being parallel. So then this means that if you tell me that V is parallel to U, according to my knowledge of vectors, I can conclude there exists a non-zero number, so that we call lambda not equals to 0. Lambda is a number such that the vector that I am looking for is lambda times U. Yes? This I understand. But then, today we learned how to calculate lambda U. If I give you the components and I ask you to calculate lambda U, you just simply multiply lambda there, yes? So this becomes the vector that I am looking for, still is missing, but I have some good information about my vector. It is lambda, 2 times lambda, 3 times lambda, yes? So the components are like this, but of course still lambda is missing. And that is exactly why they have provided us with the length of the vector. So they are demanding adjust it in a way that the length becomes 15. So it means that the length of the vector that I'm looking for is supposed to be 15. So, but I know how to calculate the length of the vector if the components are there. So this becomes square root of the first one squared, the second one squared, the third one squared is equal to 15. Then I can calculate and find lambda. So 9 plus 4 is 13, 14, yes? So then it becomes what? Square root of 14 lambda squared is equal to 15, but this means that I have to write lambda square root of 14 is equal to 15. Do you agree with that? Because if that is true, then I get one answer lambda, and then when I put that lambda here, I get one vector, but Ruben predicted correctly that we should have two vectors. So what is the problem here? Yes?
You take the square root without taking plus and minus.
Yes, you have to, no, not plus and minus, be careful. You have to put absolute value here. Yes? And then this tells me that the absolute value of lambda is equal to 15 over a square root of 14. Then I'm asking you about the number whose absolute value is this. Then it means that lambda is either plus or minus 15 over square root of 14. Yes? And then I put it back in that and I get my vector. So it means that I will have two answers for my vector. Vector v is 15 over square root of 14, 30 over square root of 14, and 45 over square root of 14. And then the other answer is the negative of these components, yes? Yes, so as we predicted, we should have two answers. So if I want to write a remark, I don't want you to memorize these things, but it's good to know. So if I write a remark for you here, it's good to see the problem in this way. I would say that let's consider vectors u with components a1, b1, and c1, and v with components a2, b2, and c2. And I emphasize that these three components are non-zero. Yes? Then we have this one. The vector u is parallel to vector v. There is a nice relation among them. So this happens in analytic form. I can write a1 over a2 is equal to b1 over b2 is equal to c1 over c2. So if you want, you can consider this as the third alternative for seeing that the vectors are parallel. So if you want to see that two vectors are parallel or not, you can calculate the ratio of the x components, the ratio of the y components, and the ratio of the z components. If all these ratios are the same, they are parallel. Yes? Okay, I want to think about the proof. The proof is very, very simple, but writing the proof will actually remind you a lot of things. So, proof exercise, yes. Just think about it. I might be using it in the future. So if two vectors are parallel, then these ratios are the same. Okay, now what is coming next? So we learned about addition, subtraction, multiplying a number by a vector in analytic form. The next operation we learn is the dot product. So we want to know that if I give you two vectors in analytic form, meaning giving you the components of two vectors, how you can calculate the dot product. That is the question, yes? And that is important actually here. Okay, so I want to do it analytically. So the question is that if I give you two vectors and I give you the components, okay? So let me from now on change the components to u u1, u2, u3 for vector u, and v1, v2, and v3. So the question is that, what is the number that I should calculate for u dot v? Yes? To do this, I have to introduce you three famous unit vectors. So let me just draw this coordinate system. The unit vector on the x-axis pointing in the same direction has a particular notation in physics or in mathematics. This is usually called I hat. Hat because this is the unit vector and this is the symbol used. But in physics I prefer to use x hat. X hat means the unit vector of the x-axis. But in mathematics usually people use I hat, meaning the same thing. So when I say I hat, it means the unit vector on the x-axis pointing in the same direction as the x-axis. And if I do the same thing for the y-axis, so you see that people easily in physics call it y hat, but in mathematics we call it j hat. And then I do the same thing here. So these are the famous unit vectors. We call it z hat or k hat. So let me stick to these notations, yes? So these are the vectors on the three axes of coordinates. Now I told you that every vector should have three components. Okay, can you tell me what are the components of vector I? What are the components of vector j? And what are the components of vector k? So I need to understand how much I am displaced on the x-axis by I, how much I am displaced on the y-axis by y, and how much I am displaced on the z-axis by y. Sorry, by I, yes? So then you can immediately write the components. So what is the x component, yes?
1, 0, 0.
Yes. So it is 1, 0, 0. And this one is what? 0, 1, 0. And this one is what? 0, 0, 1. So remember, these three vectors are very important. In 2 dimensions, we do not have k hat. We only have I hat and j hat. But we do not have the z component. So it becomes 1, 0, 0, 1. In 3 dimensions, we have these. Yes? Okay. Now, answering this question, which was a little bit hard for a generic two vectors, for generic vectors, it is easy for each pair of them. If I ask you, can you calculate I dot j, immediately you can answer. Yes? So be careful. The question is that I give you two typical vectors and I want you to calculate the dot product. I can use the word calculate because the dot product turns out to be a number at the end. But I am telling you that for these three vectors at least, you don't need any knowledge, extra knowledge. You can immediately calculate. For example, if I ask you, what is I dot j? Can you answer that? Because you have only one definition right now, and that is the old definition. The norm of the first vector multiplied by the norm of the second vector multiplied by the cosine of the angle between these two vectors. So let us follow that rule. So this becomes the norm of my first vector multiplied by the norm of my second vector and then multiplied by the cosine of the angle between these two vectors, which is 90, yes. So the angle between these two vectors is 90, so this becomes how much? The norm of this vector is 1 because the length is 1, the length is 1, cosine of 90 is 0, so it becomes 0. Or in other words, I and j are what? Are perpendicular. If they are perpendicular, the dot product should be 0. So if I ask you what happens for j dot a, that's the same because you know that's commutative. So it means that if I ask you this product for any pair of these two vectors, the answer is 0. Yes? So I dot k and j dot k, I dot j, all of them are 0. So if I take two different ones and dot product them, the answer is 0. But if I take one of them and dot product it by itself, the answer is If I dot product I by itself, then the answer is 1. Yes, it becomes the norm of the vector squared. So this becomes 1. Yes? So this is the relation among these three famous vectors of the axes. Okay. Now, why I, j, and k are so useful? Because every vector can be written as a linear combination of these three vectors. Yes? So let me ask you, if I multiply this, I, by the first component of u, u1 multiplied by I. This is meaningful, yes? I is a vector, u1 is a number, I multiply that vector by a number, it becomes a vector. And then I take the second component of that one and multiply it by j. And I take the third component of that and multiply it by k and then add them. What do you think this will be? Take the first component, multiply by I, second component by j, third component by k, and add them. What do I get at the end? You can do it in your head. Yes?
The vector u.
Do you get the vector u back? Why? Because I is this vector. If I multiply it by u1, it becomes u1 but 0, 0. If I multiply the vector j by u2, this becomes 0, u2 and 0. If I do the same thing with this, it becomes 0, 0 and u3. And if I add them, it becomes u1 plus 0, which is u1. The next one becomes u2, the next one becomes u3, and then it becomes vector u. Yes? So this is a very good thing. You can decompose every vector into three components. Let us understand this vector. This vector is actually, if I can draw it here, so if this is my vector u, this vector ui, so let me just this one, in this picture, this is easier for me to draw. So if I have, I don't know, if I have this component of that vector, this vector from here to here is actually this vector. And I have the same thing on the z-axis, this vector from here to here is the third one, and you can do the same thing for this one. So it means that if I add these three vectors, it becomes that vector. So I am decomposing a vector into its components on the axis of the coordinates. Okay, but then I can solve my problem right now. I go back and solve the problem. How? Can you tell me? So here, I want to answer the question mark. U dot v. So what is that? I have to write u dot v, but I know that u can be written in this form. So I can write it as what? u1 I hat plus u2 j hat plus u3 k hat. And I want to dot product it with the second vector v, which of course can be written as v1 I hat plus v2 j hat plus v3 k hat. I have to calculate this dot product. Okay? But I can calculate it. Do you agree? Because I know that dot product is distributive, according to what we learned before. So I can take this one and dot product it by the first one. So what will happen? It becomes u1 v1 I dot j. Is that understandable? I'm using distributive. And then, for example, I don't want to write all of them. The next one becomes u1. There would be 9 terms. 3, 3, 9 terms. So u1 v2, but I dot j. And then it will continue. Yes? Most of these terms will be 0. How many of them will survive? If you consider all cases. Yes?
Isn't the first one incorrect? I dot j.
Oh, sorry, thank you. I dot, it should be I dot I, thank you. Okay, so if I do this process, there would be 9 terms, but mainly all of them are finished except how many of them? 3 of them. Which one will survive? The first one will survive, yes, because I dot I is 1. But the second one will not survive because I dot j is 0, yes? Okay, and then what happens? So So this becomes 1, this becomes 0. So if I can continue this, I will get u1 v1. Okay, plus the next one is u2 v2, yes, agree? Because when u2 is multiplied by that one, j dot j becomes 1, and it becomes u2 v2, and then u3 v3. So that's a very simple and nice formula. So now you know the question mark, and I call it theorem. And that was the proof. So if u is this, and v is this, then u dot v has a very simple formula. It's a little bit strange. You take the first one multiplied by the first one, u1 v1. You take the second one multiplied by the second one. You take the third one multiplied by the third one and add them. That would be the number. Yes? Okay, so any questions here? So this is a theorem. Look, I cannot tell you that, okay, this is the definition. Because this definition is a little bit strange if you have the normal definition in mind, you know, the norm of a vector multiplied by the norm of this vector multiplied by the cosine of the angle between two vectors. But I hope that I could justify for you that this is indeed the case. And it is very important to memorize this formula. So if I give you two vectors and I ask you to find the dot product, this is the rule. Multiply the first components, multiply the second components, multiply the third components, and add these three numbers. The number that you get is the dot product. Okay. Now we can solve a little bit more interesting problems. So let me just give you one simple thing. So if I ask you, if I give you two vectors, 1, minus 2, and 3, and if I give you another vector v equals to 0, minus 1, minus 1, then if I ask you what is the u dot v, what I have to do, I take 1 multiplied by 0, plus I take minus 2 multiplied by minus 1, and then I will take 3 multiplied by minus 1, and it becomes a number. The number is 2 minus 3 is minus 1. So u dot v is minus 1. It's just a number. Yes? Okay. Now if I ask you find the angle between u, v, you can find that. How should I find that? I want to find, of course, you realize, is this angle between these two vectors an acute angle or an obtuse angle? Is it obtuse or acute angle? Yes?
I think it's obtuse.
Yes, because if the dot product is negative, we had this before, it is an obtuse angle. So definitely it's an obtuse angle. But if I want more than that, I want the exact value of the angle between these two vectors, what I'm supposed to do, I would say that on the one hand, u dot v is this. On the other hand, u dot v is this. Because I don't lose the old definition. Yes, I have the old definition. Okay, but the point is that now I know this number. This number is minus 1. And I know how to calculate this number. It is the square root of 1 plus 4 plus 9. And then the square root of 0 plus 1 plus 1. And the only missing part is the cosine of the angle. So then it becomes minus 1 equals to 14, square root of 14, multiplied by square root of 2 is multiplied by cosine of theta. So this means cosine of theta is minus 1 over square root of 28, which I can write it as minus 1 over 2 square root of 7. But then if I ask you what is the exact value for theta, we can say it is cosine inverse of that number. You see, combining the analytic perspective and geometric perspective gives you a little calculational abilities. Yeah? So now we can calculate the exact angle between these two vectors if I give you, and that is exactly what is here. Okay. I think that would be a good idea if we stop here, because now, let me see. Okay, let me give you one example. Okay, let us stop here, I think, because the next series of examples would be nice. We can have cover them in one session. Okay, so what is coming next, which will be a little bit harder to find an analytic form of the cross product after we did these examples. And then you should expect that is harder. Why?
Because it's become a vector.
It becomes a vector, so I should be able to introduce you 3 numbers, not 1 number. For u dot v, I only gave you 1 number, that's enough. But for the cross product, you know the answer should be a vector, so it means that I have to give you exactly how to calculate 3 numbers, not 1 number. Yes? And how to arrange them as the component of a vector. Yes, so we stop here. Thank you.